Okay, so for FRK number 1, we have a block that has a mass of 2 kilograms and it is attached to a string. This string is wrapped around a solid cylinder that has a mass of 2.5 kilograms and a radius of 0.4 meters. Now the cylinder is fixed, meaning that the block will not pull it along with it, but the cylinder is allowed to rotate. So once this block drops, the cylinder will spin. So now part A asks us to use calculus to show that the rotational inertia of the cylinder about its central axis is 1/2 mr squared. Okay, so to go about doing this, I'm going to have to start with the general form for the moment of inertia of any object, and that is I is equal to mr squared. Now, if I take the derivative of I with respect to m, I'm going to get di on this side. That's the derivative of I, and that's equal to r squared stays the same because we're taking the derivative with respect to m, and this is the derivative of m is dm. Now, if I integrate this whole equation, the integral of di is I. The integral of this side is just the integral of r squared dm, and this is the exact equation I need to for my proof. Okay, so applying this equation, my moment of inertia for a cylinder is equal to the integral of, so my r for my cylinder is capital R, so capital R squared. My mass for a cylinder is represented with a capital M, so the capital M, and so that is my equation. Okay, so now to the side, I'm going to have to try to write dm in terms of dr because I have our r squared right here, and so I want to substitute in something with dr in it so I can actually integrate this with respect to r. Okay, so first of all, I'm going to start with this equation. P is equal to, or density is equal to mass over volume. P stands for density. It is also essential that we know that the volume of the cylinder is equal to pi r squared, essentially the area of a circle times the length. Now that we have this, I'm going to substitute this in for volume. So I'm going to get density is equal to mass divided by pi r squared times length. Now I want to isolate for m. So to do that, I just multiply my denominator to this side. So my m is going to be equal to pi r squared times L times density. Now I'm going to take the derivative of m with respect to r. So this side I'm going to have the derivative of m is dm. Since I'm taking the derivative with respect to r, everything else is a constant, so everything else will stay the same. However, when I take the derivative of this, I'm going to get 2r because I bring the coefficient or the exponent out and subtract the exponent by 1. So we'll have 2r, everything stays the same. And the derivative of r is dr, so I also have that. So now that I've wrote dm in terms of dr, I can substitute in for right here. So my moment of inertia for cylinder is going to be equal to anything that is a constant can be placed outside the integral. So I'm going to place 2 outside the integral since pi outside the integral, and as well as L and P outside the integral. Now R can be grouped with this, so I have R cubed and then dr right here. dm is replaced with all of these. Okay. So now that I have this, I can integrate. Now, when I integrate basically just stays the same. Integrating this, I'm going to add 1 to my exponent, so r to the 4, and then divide by the new exponent, which is, so divide by 4. Okay, so now that I'm here, I'm going to substitute in my equation for density that I wrote before into this equation. So I'm going to have 1 I cylinder is equal to, so 2 pi times L, and here's the substitution, m divided by pi r squared times L, and then I still have a r to the 4th power divided by 4. Now there's a lot I can cancel here. I can cancel a pi with a pi right here, L with an L right here. I can also cancel an r squared with 2 r's on top, so I still have a r squared on top. 2 and 4 can be reduced down to 1/2. So now I have 1/2, I still have an m, and I have r squared. So that is exactly what I'm trying to prove. 1/2 mr squared is the moment of inertia for the cylinder. Right there. Okay. Part B has 3 parts. So the first part of part B asks us to calculate the linear acceleration of the block. Okay. So to calculate the linear acceleration of the block, I'm going to use the classic Newton equation, and that is total force is going to be equal to mass times acceleration. Now for the block, I have a force of Fg acting down, pulling the force downward, but I also have an opposing force that is tension pulling the block upward. Fg is going to be greater than tension, so it's going to come first in my equation. So Fg of the block minus T, and that's going to be equal to the mass of block times acceleration. Note that now I am writing subscripts for my masses or my m's, because in this problem we are given both the masses for the block and the cylinder is represented with a capital M, so I'm writing a subscript so I can differentiate between those two in my problem. Okay, so Fg is essentially just mass of block times gravity, and that's minus T is equal to m block times acceleration. I want to isolate for T, so I'm going to add T to this side and subtract m block A to this side. So essentially, T is going to be equal to m block times G minus m block times A. So now that I've defined T, I can use torque to help me find acceleration. So net torque, the equation for net torque is the total force that is perpendicular to the moment of arm times the moment of arm. And another equation for total torque is moment of inertia times alpha. Now in this problem, the total force that's perpendicular to the moment of arm is tension. Our moment of arm is capital R, and then our I is I cylinder, and we have alpha. Now alpha, or angular acceleration, is equal to acceleration divided by radius, and this I can substitute in for angular acceleration in the following step. I can also substitute this in for T, and I can also substitute this in for I cylinder. So here goes a bunch of substitution. So first T, I'm going to substitute this in, m block G minus M block A times A times R on the outside, and that's going to equal to, so R of cylinder is 1/2 mass of cylinder times R squared, and then angular acceleration is A over R. So at this point, I can cancel out all my R's. One R can cancel out with one R over here, and leaving one R left, and that one R left will cancel out with the one R from the bottom right here. So all my R's cancel out. Now I can plug in all my numbers. So 2 kilograms is my block, massive block. 9.8 meters per second is meters per second squared is my G. Again, massive block is 2 kilograms. A is what we're trying to solve for, and that's going to be equal to 1/2 massive cylinder is 2.5 kilograms. And A is what we're trying to solve for. This reduces down to 19.6. This is minus 2A, and this reduces down to 1.25A. Now I'm going to combine like terms by adding 2A to this side. So I'm going to get 19.6 is equal to 2A plus 1.25A is 3.25A. Now solving for A, I'm going to divide 3.25 to this side, and plug that into the calculator. I'm going to get A is equal to 6.031 meters per second squared. So that is the acceleration of the block. Okay, now that I've solved for acceleration of the block, that paves the way for solving the other two in an easy manner. So the second part asks me to calculate the net torque exerted on the cylinder. Okay, so let's see. As a reminder, the equation for net torque on a cylinder is the moment of inertia of the cylinder times alpha. Okay, I cylinder is 1/2 M cylinder times R squared, and alpha is up here is A over R. The one R will cancel out with the one R on top, and so I can plug in my numbers now. So 1/2 mass of cylinder is 2.5 kilograms. My radius is 0.4 meters, and my acceleration I just found up here is 6.31 meters per second squared. Plug this into your calculator, I get 3.015, and my units is newtons times meters. The third part of part B asks me to calculate the tension of the string. This is easy because I've already defined tension of the string here, and I have all the numbers for it, so I can just plug them in. So as a reminder, I'm just going to write down the equation for tension of the string that I defined up there, and that is mass of block times G minus mass of block times A. Now I'm going to plug in my numbers. So mass of block is 2 kilograms. G is 9.8 meters per second squared. Minus mass of block is 2 kilograms once again. Acceleration we found up here is 6.31 meters per second squared. Plug this into the calculator, we're going to get 7.538, and our units is newtons. Okay. Now part C tells us that at time ts, the block reaches the lowest point and the string is completely unwounded. The string then begins to rewind on the cylinder, and the mass is raised back upward. And now it tells us to graph the scenario that this happened. So, before TS and after TS. Okay, so graph C. Okay, so before TS, or before the string completely unwinds, the angular momentum. Wait, this is an angular momentum graph versus time, by the way. Okay, so I know that in the first part, my graph is going to be linear because my angular momentum is by definition is going to be equal to my I cylinder times omega. Now my omega is equal to my alpha times t. So if I substitute this in, I'm going to get I cylinder times alpha times t. Now I cylinder and alpha are constants. A constant with a t with no power is just a straight line, so it's a linear slope. Okay, so that is the first part of. Now, after the string has completely unwound, it will wind back up, and now this is what it's gonna look like. So the string will be right here when it's completely unwound, but then once it winds back up, it's going to be something like this, and the cylinder is going to still rotate this way, but then the force of the tension is going to generate a torque that is opposing it. So essentially, this will cause the angular momentum to slow down at a constant rate. So that lets me know that after TS, my angular momentum will start to lower. So it looks something like this. And there's my graph. Okay, part D, we are asked if the block is replaced, if the solid cylinder is replaced with a hollow cylinder, how would that affect the time when it completely unwinds? So is TH going to be greater, equal to, or less than TS? So my answer is that TH is going to be greater than TS. That means that the time that it takes for the hollow cylinder, the string around the hollow cylinder to completely unwound is going to take more time for that string to unwound than for the solid cylinder. And here's why. So a hollow cylinder would have a higher moment of inertia, higher I moment of inertia than a solid cylinder, because more of the hollow cylinder's mass will be concentrated farther away from the axis of rotation. Now, having a higher I means that the hollow sphere, or the hollow cylinder would be more resilient to change, or more resistant to change. Thus, it will have a smaller angular acceleration. A smaller angular acceleration means that the hollow cylinder will gain angular velocity slowly, more slowly, and take more time to unwind. So that's my explanation.